level. Maybe just a quick, in broad strokes, from your perspective, what is you were, speaking of inspiration, the president of the Society for Industrial and Applied Mathematics.
Oh, yes.
It's a major organization in math and applied math. What do you see as the role of that society, in our public discourse?
Right.
In public.
Yeah. So, well, it was fun to be president at the at the time.
Couple of years, 2 years.
2 years around 2000. So as president of a pretty small society, but nevertheless, it was a time when math was getting some more attention in Washington. But yeah, I got to give a little 10 minutes to a committee of the House of Representatives,
Nice.
talking about why math. And then actually it was fun because one of the members of the House had been a student, had been in my class. What do you think of that? Yeah, as you say, it's pretty rare. Most members of the House have had a different training, different background, but there was one from New Hampshire who was my friend, really, by being in the class. Yeah, so those years were good. Then, of course, other things take over in importance in Washington, and math just at this point is not so visible. But for a little moment, it was.
There's some excitement, some concern about artificial intelligence in Washington now.
Yes,
about the future.
Yeah,
and I think at the core of that is math.
Well, it is, yeah.
I mean, but maybe it's hidden. Maybe it's wearing a different hat.
Well,
but
right. Well, artificial intelligence, and particularly, can I use the words deep learning?
Yeah.
Deep learning is a particular approach to understanding data. Again, you've got a whole lot of data, where data is just swamping the computers of the world, and to understand it, out of all those numbers, to find what's important, in climate, in everything. And artificial intelligence is two words for one approach to data. Deep learning is a specific approach there, which uses a lot of linear algebra. So I got into it. I thought, okay, I've got to learn about it.
Where does linear algebra sit as a subfield of mathematics? What are the various subfields that you think about in relation to linear algebra?
So the big fields of math are algebra as a whole, and problems like calculus and differential equations. So that's a second quite different field. Then maybe geometry. It deserves to be thought of as a different field to understand the geometry of high-dimensional surfaces. So I think, am I allowed to say this here? I think this is where personal view comes in. I think math, for thinking about undergraduate math, what millions of students study, I think we overdo the calculus at the cost of the algebra, at the cost of linear.
So you have this talk titled "Calculus versus Linear Algebra."
That's right.
And you say that linear algebra wins. So can you dig into that a little bit? Yeah. Why does linear algebra win?
Right. Well, okay. The viewer is going to think this guy is biased. Not true. I'm just telling the truth as it is. Yeah. So I feel linear algebra is just a nice part of math that people can get the idea of. They can understand something that's a little bit abstract, because once you get to 10 or 100 dimensions, and very, very, very useful. That's what's happened in my lifetime, is the importance of data, which does come in matrix form. So it's really set up for algebra. It's not set up for differential equations. And let me fairly add probability. The ideas of probability and statistics have become very, very important, have also jumped forward. So, and that's different from linear algebra, quite different. So now we really have three major areas to me: calculus, linear algebra, matrices, and probability statistics. And they all deserve a important place. And calculus has traditionally had a lion's share of the time.
A disproportionate share.
Thank you. Disproportionate. Yeah. That's a good word.
Of the love and attention from the excited young minds.
Yeah.
What to you is beautiful about mathematics?
I love a mathematics that some people don't even think of as mathematics, which is beautiful, creative mathematics, where we look at maths in different ways, we visualize it, we think about different solutions to problems. A lot of people think of maths as you have one method and one answer. And what I love about maths is the multiple different ways you can see things, different methods, different ways of seeing, in some cases, different solutions. So that is what is beautiful to me about mathematics, that you can see and solve it in many different ways. And also the sad part that many people think that maths is just one answer and one method.
Mm-hmm. So to you, the beauty emerges when you have a problem with a solution and you start adding other solutions, simpler solutions, weirder solutions, more interesting, some that are visual, some that are algebraic, geometry, all that kind of stuff.
Yeah. I mean, I always say that you can take any maths area and make it visual. Mm-hmm. And we say to teachers, give us your most dry, boring maths and we'll make it a visual, interesting, creative problem. And it turns out you can do that with any area of maths. And I think it's been a great disservice to kids and others that it's always been numbers, lots and lots of numbers. Numbers can be great, but you can think about maths in other ways besides numbers.
Do you find that most people are better visual learners, or is this just something that's complementary? What's the kind of the full spectrum of students in the way they like to explore math, would you say?
I mean, there's definitely people who come into the classes I do who are more interested in visual thinking and like visual approaches. But it turns out what the neuroscience is telling us is that when we think about maths, there are two visual pathways in the brain, and we should all be thinking about it visually. Some approaches have been to say, well, you're a visual learner, so we'll give you visuals, and you're not a visual learner. But actually, if you think you're not a visual learner, it's probably more important that you have a visual approach so you can develop that part of your brain.
So you were saying that there's some kind of interconnected aspect to it. So the visual connects with the non-visual.
Yeah. So this is what the neuroscience has shown us, that when you work on a maths problem, there are 5 different brain pathways, and that the most high achieving people in the world are people who have more connections between these pathways. Mm-hmm. So if you see a maths problem with numbers, but you also see it visually, that will cause a connection to happen in your brain between these pathways. And if you maybe write about it with words, that would cause another connection. Or maybe you build it with something physical, that would cause a different connection. And what we want for kids is, we call it a multi-dimensional experience of maths, seeing it in different ways, experiencing it in different ways. That will cause that great connected brain.
You know, there's these stories of physicists doing the same. I find physicists are often better at building that part of their brain of using visualization for intuition building, because you ultimately want to understand the deepest secret underneath this problem, and for that you have to intuit your way there.
Yeah.
And you mentioned offline that one of the ways you might approach a problem is to try to tell a story about it. And some of it is like legend, but I'm sure it's not always. You have Einstein thinking about a train, and the speed of light, and that kind of intuition is useful.
Yeah.
You start to imagine a physical world, how does this idea manifest itself in the physical world, and then start playing in your mind with that physical world and think, is this going to be true? Is this going to be true?
Right. Einstein is well known for thinking visually. And people talk about how he really didn't want to go anywhere with problems without thinking about them visually. But the other thing you mentioned that sparked something for me is thinking with intuition, like having intuition about maths problems. That's another thing that's often absent in maths class, the idea that you might think about a problem and use your intuition, but so important. And when mathematicians are interviewed, they will very frequently talk about the role of intuition in solving problems, but not commonly acknowledged or brought into education.
Yeah. I mean, that's what it is. Like, if you task yourself with building an intuition about a problem, that's what you start to pull in, like, what is the pattern I'm seeing? In order to understand the pattern, you might want to then start utilizing visualization. But ultimately, that's all in service of, like, solving the puzzle, like cracking it open to get the simple explanation of why things are the way they are, as opposed to, like you said, having a particular algorithm that you can then execute to solve the problem. Yeah, but it's hard. It's hard.
Yeah.
Like, reasoning is really hard.
Yeah, it's hard. I mean, I love to value what's hard in maths instead of being afraid of it. We know that when you struggle, that's actually a really good time for your brain. You want to be struggling when you're thinking about things. So if it's hard to think intuitively about something, that's probably a really good time for your brain. I used to work with somebody called Sebastian Thrun, who is a great sort of mathematician. You might think of him an AI person. And I remember in one interview I did with him, he talked about how they'd built robots, I think for the Smithsonian, and how they were having this trouble with them picking up white noise. And he said they had to solve it. They had to work out like what's going on, and how he intuitively worked out what the problem was. But then it took him 3 weeks to show it mathematically. I thought that was really interesting, that how you can have this intuition and know something works. It's kind of different from going through that long mathematical process of proving it, but so important.
Yeah. I think probably our brains are evolved as like intuition machines, and the math of like showing it like formally is probably an extra thing that we're not designed for. You see that with Feynman and his I mean, it just, all of these physicists, definitely you see starting with intuition, sometimes starting with an experiment, and then the experiment inspires intuition. But you can think of an experiment as a kind of visualization.
Right.
Just like, let's take whatever the heck we're looking at and draw it, and draw like the pattern as it evolves, as the thing grows, for n equals 1, for n equals 2, n equals 3, and you start to play with it. And then in the modern day, which I loved doing, is, you can write a program that then visualizes it for you.
Right.
And then you can start exploring it programmatically. And then you can do so interactively too. I tend to not like interactive because it takes way too much work, because you have to click and move and stuff. I love to interact through writing programs, but that's my particular brain, software engineer. So like you can do all these kinds of visualizations, and then there's the tools of visualization like color, all of those kinds of things.
Yeah.
That you're absolutely right. They're actually not taught very much.
Right.
Like the art of visualization.
Not taught. And we love as well color coding. Like when you represent something mathematically, you can show color to show the growth.
Yeah.
And kind of code that. So if I have an algebraic expression for a pattern, maybe I show the X with a certain color, but I also write in that color so you can see the relationship. Very cool. And we, particularly in our work with elementary teachers, many of them come to our workshops and they're literally in tears when they see things making sense visually, because they've spent their whole lives not realizing you can really understand things with these visuals. It's quite powerful.
Those early few days when you just want to capture them.
I do something, actually there's a video of me doing this on our website that I love when I first meet students. And this is what I do. I show them a picture. This is the picture I show them. And it's a picture of 7 dots like this. And I show it for just a few seconds. And I say to them, I'd like you to tell me how many dots there are, but I don't want you to count them. I want you to group the dots. And I show it them, and then I I take it away before they've even had enough time to count them. And then I ask them, so how did you see it? And I go around the room, and amazingly enough, there's probably 18 different ways of seeing these 7 dots. Mm-hmm. And so I asked people, tell me how you grouped it. And some people see it as like an outside hole with a center dot. Mm-hmm. Some people see like stripes of lines. Some people see segments. And I collect them all and I put them on the board. And at the end, I say, look at this. We are a class of 30 kids and we saw these 7 dots in 18 different ways. There's actually a mathematical term for this. It's called groupitizing.
Groupitizing?
Yeah.
I like it.
It's kind of cool. So turns out, though, that how well you groupitize predicts how well you do in maths.
Is it a raw talent, or is it just something that you can develop?
I don't think it's raw. I don't think you're born groupitizing, I think. But some kids have developed that ability, if you like, and you can learn it. So this, to me, is part of how wrong we have maths, that we think to tell whether a kid's good at maths, we're going to give them a speed test on on multiples. But actually, seeing how kids group dots could be a more important assessment of how well they're going to do in maths. Anyway, I diverge. What I like to do, though, when I start off with kids is show them, I'm going to give you maths problems. I'm going to value the different ways you see them. And turns out you can do this kind of problem asking people how they group dots with young children or with graduate students. And it's engaging for all of them.
You talk about creativity a little bit and flexibility in your book, Limitless. What's the role of that? So it sounds like there's a bit of that kind of thing involved in groupitizing.
Yeah. Yeah.
I love this term. So what would you say is the role of creativity and flexibility in the learning of math?
I think what we know now is that what we need for this 21st century world we live in is a flexible mind. School should not really be about teaching kids particular methods, but teaching them to approach problems with flexibility. Being creative, thinking creatively is really important. So people don't think the words maths and creativity come together, but that's what I love about maths, is the creative different ways you can see it. And so helping our kids, there's a book I like a lot written by physicists. You probably know this book called Elastic. Or you might know it. And it's about how we want elastic minds. Same kind of thing. Flexible, creative minds. And schools do very little on developing that kind of mind. They do a lot of developing the kind of mind that a computer now does for us.
Memorization,
doing procedures, a lot of things that we spend a lot of time in school on. In the world, when kids leave school, a computer will do that. And better than they will. But that creative, flexible thinking, we're kind of at ground zero at computers being able to engage in that thinking. Maybe we're a little above ground zero, but the human brain is perfectly suited for that creative, flexible thinking. That's what humans are so great at. So I would like the balance to shift in schools. Maybe you still need to do some procedural kind of thinking, but there should be a lot more of that creative, flexible thinking.
And what's the role of other humans in this picture? So collaborative learning, so brainstorming together, so creativity as it emerges from the collective intelligence of multiple humans.
Yeah, super important. And we know that also helps develop your brain, that social side of thinking. And I love mathematics collaboration, where people build on each other's ideas and they come up with amazing things. I actually taught 100 students calculus at Stanford recently, undergrads, and we taught them to collaborate. So these students came in Stanford and most of them were against collaboration in maths.
This is before COVID in person?
Yeah, it was just before COVID hit. It was 2019. And the summer.
Sorry, you said they're against?
So it's really interesting. So they'd only experienced maths individually, as in a kind of competitive individual way. Yeah. And if they had experienced it as group work, it had been a bad experience. Like maybe they were the one who did it all and the others didn't do much. So they were kind of against collaboration. They didn't see any role for it in maths. And we taught them to collaborate. And it was hard work because as well as the fact that they were kind of against collaboration, they came in with a lot of like social comparison thinking. So I'm in this room with other Stanford undergrads and they're better than me. So when we set them to work on a maths problem together, the first one was kind of a disaster because they were all like, they're better than me, they're faster than me. They came up with something I didn't come up with. Yeah. So we taught them to let go of that thinking and to work well together. And one of the things we did, we decided we wanted to do a pre and post test at the end of this teaching. It was only 4 weeks long. But we knew we didn't want to give them like a time test of individual work. So we gave them an applied problem to do at the beginning. And we gave them to do in pairs together. And we gave each of them a different colored pen and said, work on this activity together and keep using that pen. So then we had all these pieces of student work. And what we saw was they just worked on separate parts of the paper. So there's a little like red pen section and a green pen section. And they didn't do that well on it, even though it was a problem that middle or high school kids could do, but it was like a problem solving kind of problem. And then we gave them the same one to do at the end, gave them the same colors, and they had learned to collaborate. And not only were they collaborating the second time around, but that boosted their achievement. And the ones who collaborated did better on the problem. Collaboration is important, having people, and what was so eye-opening for these undergrads, and they talked about it in lovely ways, was I learned to value other people's thinking on a problem. And I learned to value that other people saw it in different ways. And it was quite a big experience for them, that they came out thinking, I can do maths with other people. People can see it differently. We can build on each other's ways of thinking.
I got a chance to, I don't know if you know who Daniel Kahneman is. Got a chance to interact with him. Mm-hmm. And like the first, because he had a few, but one famous collaboration throughout his life with Tversky. And just like, he hasn't met me before in person, but just the number of questions he was asking, just the curiosity. So I think one of the skills, the collaboration itself is a skill. And I remember my experience with him was like, okay, I get why you're so good at collaboration, because he was just extremely good at listening and genuine curiosity about how the other person thinks about the world, sees the world. And then together, he pulled me in that particular case. He doesn't know in particular like that much about autonomous vehicles, but he kept like asking all of these questions, and then like 10 minutes in, we're together trying to solve the problem of autonomous driving. And that, I mean, that's really fulfilling, that's really enriching, but it also in that moment made me realize it's kind of a skill, because you have to kind of put your ego aside, put your view of the world aside, and try to learn how the other person sees it.
And the other thing you have to put aside is this social comparison thinking. Like if you are sitting there thinking, wow, that was an amazing idea, he's so much better than I am, that's really going to stop you taking on the value of that idea. And so there was a lot of that going on between these Stanford students when they came. And but trying to help them let go of that.
One of the things I've discovered, just because being a little bit more in the public eye, how rewarding it is to celebrate others.
Yeah.
And how much is going to actually pay off in the long term.
Yeah.
So this kind of silo thinking of like, I want to prove to a small set of people around me that I'm really smart, and do so by basically not celebrating how smart the other people are. That's actually maybe short term, it seems like a good strategy, but long term it's not. And I think if you practice at the student level and then at the career level, at every single stage, I think that's ultimately...
I agree with you. I think that's a really good way of thinking about it.
You mentioned textbooks, and you didn't say it, maybe textbooks isn't the perfect way to teach mathematics. But I love textbooks. They're like pretty pictures and they smell nice and they open. I mean, I talk about like physical. Some of my greatest experiences have been just like, because they're really well done. When we're talking about basic like high school calculus, biology, chemistry, those are incredible. It's like Wikipedia, but with color and nice little.
You must have seen some good textbooks if they had pretty pictures and color.
Yeah, I mean, I remember. I guess it was very, very standard, like AP calculus, AP biology, AP chemistry. I felt those are like some of the happiest days of my life in terms of learning was high school, because it's very easy. Honestly, it felt hard at the time, but you're basically doing a whirlwind tour of all of science.
Yeah. Yeah.
Without having to pick. You do like literature, you do like Shakespeare, you do calculus, biology, physics, chemistry, what else? Anatomy, physiology, computer science. Without like, nobody's telling you what to do with your life. You're just doing all of those things.
That's a good thing. You're right.
But I remember the textbooks weren't, I mean, maybe I'm romanticizing the past, but I remember they weren't, they're pretty good. But so you think, what role do you think they play still in like in this more modern digital age? What's the best materials with which to do these kinds of educations?
Yeah. Well, I'm intrigued that you had such a good experience with textbooks. I mean, I can remember loving some textbooks I had when I was learning, and I love books. I love to pick up books and look through them. But a lot of maths textbooks are not good experiences for kids. We have a video on our website of the kids who came to our camp, and one of the students says, in maths, you have to follow the textbook. The textbook's kind of like the Bible. You have to follow it. And every day, it's slightly different. Like on Monday, you do 2.3.2, and on Tuesday, you do 2.3.3, and on Wednesday. And you never go off that. That's like every single day. And that's not inspiring for a lot of the kids. So one of the things they loved about our camp was just that there were no books. Even though we gave them sheets of paper instead, they still felt more free because they weren't just like trotting through exercises. So
like what a textbook allows you is like the very thing you said they might not like, the 2.3, it feels like you're making progress, and like it's little celebrations because you do the problem and it seems really hard and you don't know how to do it, and then you try and then eventually succeed, and then you make that little step and further progress, and then you get to the end of a chapter and you get to like it's closure. You're like, all right, I got that figured out, and then you go on to the next chapter.
I can see that. I mean, I think it could be in a textbook. You can have a good experience with a textbook, but what's really important is what is in that textbook. What are you doing inside it? And I mean, I grew up in England, and in England we learn maths. We don't have this separation of algebra and geometry, and I don't think any other country apart from the US has that. But I look at kids in algebra classes where they're doing algebra for a year, and I think I would have been pretty bored doing that.
By the way, can we analyze your upbringing real quick? Why do British folks call mathematics maths? Why is it the plural? Is it because of everything you're saying, where it's a bunch of subdisciplines?
Yeah, I mean, mathematics is supposed to be the different maths that you look at. Whether you think of that as topics like geometry and probability, or I think of it as maths is just multidimensional, lots of ways. But that's why it was called mathematics, and then it was shortened to maths, and then for some reason it was just math in the US. But to me, math has that more singular feel to it, and there's an expression here which is do the math. Which basically means do a calculation. That's what people mean by do the math. So I don't like that expression because, math could be anything. It doesn't have to be a calculation. And So yeah, I like maths because it has more of that broad feel to it.
Yeah, I love that. Maths kind of emphasizes the multidimensional, like the variety of different, the subdisciplines, different approaches. Yeah. Okay. But outside of the textbook, what do you see like broadly being used? You mentioned Sebastian Thrun and MOOCs, like online education. Do you think that's an effective set?
Can be. I mean, online, having great teachers online obviously extends those teachers to many more people, and that's a wonderful thing. I have quite a few online courses myself. I got the bug working with Sebastian when he had released his first MOOC. And I thought, maybe I could do one in maths education. And I didn't know if anybody would take it. I remember releasing it that first summer, and it was a free online class, and 30,000 maths teachers took it that first summer. And they were all talking about it with each other and sharing it. And it was like, took off. In fact, it was that MOOC that got me to create UCubed with Kathy Williams, who's the co-founder, because people took the MOOC and then they said, okay, what now? Like, I finished, what can I have next? And so that was why we made our website. But so yeah, I think online education can be great. I do think a lot of the MOOCs don't have great pedagogy. They're just a talking head. And you can actually engage people in more active ways, even in online learning. So I learned from the Udacity principle when I was working at Udacity, never to talk more than like 5 minutes, and then to ask people to do something. So that's the sort of pedagogy of the online classes I have. There's a little bit of presenting something and then people do something, and there's a little bit more, because I think if you have a half-hour video, you just switch off and start doing other things.
So the way Udacity did it is like 5-10 minute like bit of teaching, and then with some visual stuff perhaps, and then there's like a quiz almost.
Then you answer a question. Yeah.
No, that's really. What is the most beautiful or awe-inspiring idea you've come across in mathematics?
I don't know, man.
Maybe it's an idea you've explored in your videos, maybe not. What like just gave you pause?
It's the most beautiful idea.
Small or big?
So I think often the things that are most beautiful are the ones that you have like a little bit of understanding of, but certainly not an entire understanding. It's a little bit of that mystery that is what makes it beautiful.
Almost a moment of the discovery for you personally, almost just that leap of the aha moment.
So something that really caught my eye, I remember when I was little, there were these like, I think the series was called like Wooden Books or something, these tiny little books that would have just a very short description of something on the left and then a picture on the right. I don't know who they're meant for, but maybe it's like loosely children or something like that. But it can't just be children because of some of the things I was describing. On the last page of one of them, somewhere tiny in there was this little formula that on the left hand had a sum over all of the natural numbers. You know, it's like 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, on and on to infinity. Then on the other side had a product over all of the primes. And it was a certain thing that had to do with all the primes. And like any good young math enthusiast, I'd probably been indoctrinated with how chaotic and confusing the primes are, which they are. And seeing this equation where on one side you have something that's as understandable as you could possibly get, the counting numbers.
Yes.
And on the other side is all the prime numbers. It was like this, whoa, they're related like this? There's a simple description that includes like all the primes getting wrapped together like this. This is like the Euler product for the zeta function, as I like later found out. The equation itself essentially encodes the fundamental theorem of arithmetic, that every number can be expressed as a unique set of primes. Mm-hmm. To me, still, I certainly don't understand this equation or this function all that well. The more I learn about it, the prettier it is. The idea that you can, this is sort of what gets you representations of primes, not in terms of primes themselves, but in terms of another set of numbers that are like the non-trivial zeros of the zeta function. And again, I'm very kind of in over my head in a lot of ways as I like try to get to understand it. But the more I do, it always leaves enough mystery that it remains very beautiful to me.
So whenever there's a little bit of mystery just outside of your understanding, that and by the way, the process of learning more about it, how does that come about? Just your own thought, or are you reading?
Reading, yeah.
Or is the process of visualization itself revealing more to you?
Visuals help. I mean, in one time when I was just trying to understand like analytic continuation and playing around with visualizing complex functions, this is what led to a video about this function. It's titled something like Visualizing the Riemann Zeta Function. Mm-hmm. It's one that came about because I was programming and tried to see what a certain thing looked like. And then I looked at it. I'm like, whoa, that's elucidating. And then I decided to make a video about it. But I mean, you try to get your hands on as much reading as you can. You know, in this case, I think if anyone wants to start to understand it, if they have like a math background of some, like they studied some in college or something like that, like the Princeton Companion to Math has a really good article on analytic number theory. And that itself has a whole bunch of references. And, you know, anything has more references and it gives you this like tree to start pawing through. And like, you know, I try to understand things visually as I go. That's not always possible, but it's very helpful when it does. You recognize when there's common themes. Like in this case, cousins of the Fourier transform like come into play, and you realize, oh, it's probably pretty important to have deep intuitions of the Fourier transform, even if it's not explicitly mentioned in like these texts. And you try to get a sense of what the common players are. But I'll emphasize again, like I feel very in over my head when I try to understand the exact relation between like the zeros of the Riemann zeta function and how they relate to the distribution of primes. I definitely understand it better than I did a year ago. I definitely understand it 1/100th as well as the experts on the matter do, I assume. But the slow path towards getting there it's fun, it's charming, and like to your question, very beautiful.
And the beauty is in the journey versus the destination?
Well, it's that each thing doesn't feel arbitrary. I think that's a big part, is that you have these these very unpredictable patterns or these intricate properties of like a certain function. But at the same time, it doesn't feel like humans ever made an arbitrary choice in studying this particular thing. Mm-hmm. So, you know, it feels like you're speaking to patterns themselves or nature itself. That's a big part of it. I think things that are too arbitrary, it's just hard for those to feel beautiful because this is sort of what the word contrived is meant to apply to, right?
And when they're not arbitrary means it could be, you can have a clean abstraction and intuition that allows you to comprehend it.
Well, to one of your first questions, it makes you feel like if you came across another intelligent civilization, that they'd be studying the same thing. Right?
Maybe with different notation, but
certainly, yeah. But yeah, like that's what I think. You talk to that other civilization, they're probably also studying the zeros of the Riemann zeta function, or like some variant thereof that is like a clearly equivalent cousin or something like that. But that's probably on their docket.
Yeah,
let's talk about that. You mentioned that earlier. What the heck is mathematics? And
okay, so So what is mathematics? Mathematics, sort of at a lowest level, one thinks of mathematics as you have certain axioms. You say things like x plus y is the same as y plus x. That's an axiom about addition. And then you say we got these axioms, and from these axioms we derive all these theorems that fill up the literature of mathematics. The activity of mathematicians is to derive all these theorems. Actually, the axioms of mathematics are very small. You can fit, when I did my New Kind of Science book, I fit all of the standard axioms of mathematics on basically a page and a half. It's not much stuff. It's like a very simple rule from which all of mathematics arises. The way it works, though, is a little different from the way things work in sort of a computation, because in mathematics, what you're interested in is a proof. And the proof says, from here, you can use, from this expression, for example, you can use these axioms to get to this other expression. So that proves these two things are equal. Okay, so we can begin to see how this is going to work. What happen is there are paths in metamathematical space. So what happens is each, two different ways to look at it. You can just look at it as mathematical expressions, or you can look at it as mathematical statements, postulates or something. But either way, you think of these things, and they are connected by these axioms. So in other words, you have some fact, you have some expression, you apply this axiom, you get some other expression. And
in general, given some expression, there may be many possible different expressions you can get. You basically build up a multi-way graph. Mm-hmm. And a proof is a path through the multi-way graph that goes from one thing to another thing. The path tells you how did you get from one thing to the other thing. It's the story of how you got from this to that. The theorem is the thing at one end is equal to the thing at the other end. The proof is the path you go down to get from one thing to the other.
You mentioned that Gödel's incompleteness theorem is not natural. It fits naturally there. How does it fit?
So what happens there is that the Gödel's theorem is basically saying that there are paths of infinite length. That is, that there's no upper bound. If you know these two things, you say, I'm trying to get from here to here, how long do I have to go? You say, well, I've looked at all the paths of length 10. Somebody says, that's not good enough. That path might be of length 1 billion. And there's no upper bound on how long that path is. And that's what leads to the incompleteness theorem. So, I mean, the thing that is kind of an emerging idea is you can start asking, what's the analog of Einstein's equations in metamathematical space? Mm-hmm. What's the analog of a black hole in metamathematical space?
What's the hope? So, yeah, it's fascinating to model all the mathematics in this way.
So here's what it is. This is mathematics in bulk. So human mathematicians have made a few million theorems. They've published a few million theorems. But imagine the infinite future of mathematics. Apply something to mathematics that mathematics likes to apply to other things. Take a limit. What is the limit of the infinite future of mathematics? What does it look like? What is the continuum limit of mathematics? What is as you just fill in more and more and more theorems, what does it look like? What does it do? What kinds of conclusions can you make? So, for example, one thing I've just been doing is taking Euclid. So Euclid, very impressive. He had 10 axioms. He derived 465 theorems. Mm-hmm. Okay. His book, that was the sort of defining book of mathematics for 2,000 years. Mm-hmm. So you can actually map out, and I actually did this 20 years ago, but I've done it more seriously now. You can map out the theorem dependency of those 465 theorems. So from the axioms, you grow this graph, it's actually a multi-way graph, of how all these theorems get proved from other theorems. And so you can ask questions about, you can ask things like, what's the hardest theorem in Euclid? The answer is, the hardest theorem is that there are 5 Platonic solids. That turns out to be the hardest theorem in Euclid. That's actually his last theorem in all his books. That's the final.
What's the hardness? The distance you have to travel?
Yeah, it's 33 steps from the longest path in the graph is 33 steps. So that's there's a 33-step path you have to follow to go from the axioms, according to Euclid's proofs, to the statement there are 5 Platonic solids. So then the question is, what does it mean if you have this map? Okay, so in a sense, this meta-mathematical space is the infrastructural space of all possible theorems that you could prove in mathematics. Mm-hmm. That's the geometry of meta-mathematics. There's also the geography of mathematics. That is, where did people choose to live in space? And that's what, for example, in exploring the sort of empirical meta-mathematics of Euclid is doing.
You could put each individual, like, human mathematician, you can embed them into that space. I mean, they kind of
they represent a path.
The little
space,
path.
The things they do.
Maybe a set of paths.
Right.
So a set of axioms that are chosen.
When you think about learning and intelligence, maybe thinking about the human brain and trying to describe mathematically the process of learning, that is something like what happens in the human brain. Do you think we have the tools currently? Do you think we will ever have the tools to try to describe that process of learning?
It is not descriptions what's going on. It is interpretation. It is your interpretation. Your vision can be wrong. When guy invent microscope, Leeuwenhoek, for the first time, only he got this instrument and he kept secret about microscope. But he wrote report in London Academy of Science. And in his report, when he looking at the blood, he look everywhere, on the water, on the blood, on the sperm. But he described blood like fight between queen and king. Mm-hmm. So he saw blood cells, red cells, and he imagined that it is army fighting each other. And it was his interpretation of situation. And he sent this report in Academy of Science. They very carefully look because they believe that he's right. He saw something,
Yes.
but he gave wrong interpretation. And I believe the same can happen to his brain.
With
Because
brain, yeah.
the most important part, I believe in human language. In some proverb is so much wisdom. For example, people say that it is better than 1,000 days of diligent studies one day with great teacher. But if I will ask you what teacher does, nobody knows. And that is intelligence. But we know from history and now from math and machine learning that teacher can do a lot.
So what, from a mathematical point of view, is the great teacher? Maybe just me, but in all the math you show, in your work, which is some of the most profound mathematical work in the field of learning AI and just math in general, I hear a lot of poetry and philosophy. You really kind of talk about philosophy of science. There's a poetry and music to a lot of the work you're doing and the way you're thinking about it. So where does that come from? Do you escape to poetry? Do you escape to music?
I think that there exists ground truth.
There exists ground truth?
Yeah, and that can be seen everywhere.
Yeah.
The smart guy philosophers, sometimes I surprise how they deep see. Sometimes I see that some of them are completely out of subject. Mm-hmm. But the ground truth I see in music.
Music is the ground truth?
Yeah. And in poetry, many poets, they believe that they take dictation.
So what piece of music, as a piece of empirical evidence, gave you a sense that they are they're touching something in the ground truth?
It is structure.
The structure of the
yeah, because when you're listening to Bach,
Bach,
you see this structure.
Yeah.
Very clear, very classic, very simple. Yeah. And the same in math, when you have axioms in geometry, you have the same feeling.
Yeah.
And in poetry, sometimes you see the same.
Yeah. And if you look back at your childhood,
I don't know.
That's an open question.
But we can say what teacher can do. He can introduce some invariants, some predicate for creating invariants. How he doing it, I don't know, because teacher knows reality and can describe from this reality a predicate, invariants. But we know that when you're using invariant, you can decrease number of observations 100 times. That's
so. But maybe try to pull that apart a little bit. I think you mentioned like a piano teacher saying to the student, "Play like a butterfly." Yeah. Right. I played piano. I played guitar for a long time, and there's maybe it's romantic, poetic. But it feels like there's a lot of truth in that statement. Like there is a lot of instruction in that statement. And so can you pull that apart? What is that? The language itself may not contain this information.
It's not blah, blah, blah. Because
it is not blah, 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 yeah.
Affect you.
It's what?
Affect you.
Yeah.
Affect your playing.
Yes, it does. But it's not the it feels like what is the information being exchanged there? What is the nature of information? What is the representation of that information?
I believe that it is sort of predicate, but I don't know. That is exactly what intelligence.
So let me just step back a little bit first to talk about. You mentioned, which I read last night, the parts of the 1960 paper by Eugene Wigner. Yeah. Unreasonable effectiveness of mathematics and natural sciences. Such a beautiful paper.
Yeah,
by the
absolutely.
way, it made me feel, to be honest, to confess my own work in the past few years on deep learning, heavily applied, made me feel that I was missing out on some of the beauty of nature in the way that math can uncover. So let me just step away from the poetry of that for a second. How do you see the role of math in your life? Is it a tool? Is it poetry? Where does it sit? And does math for you have limits of what it can describe?
Some people saying that math is language which use God. So I believe
speak to God or use God or
use God.
Use God.
Yeah. So I believe that this article about effectiveness, unreasonable effectiveness of math, is that if you're looking at mathematical structures, they know something about reality. And the most scientists from natural science, they're looking on equation and trying to understand reality. So the same in machine learning. If you trying very carefully look on all equations which define conditional probability, you can understand something about reality more than from your fantasy.
You write about modeling of mathematical cognition. So let me first ask about mathematics in general. There's a paper titled Parallel Distributed Processing Approach to Mathematical Cognition, where in the introduction there's some beautiful discussion of mathematics. And you reference there Tristan Needham, who criticizes a narrow formal view of mathematics by likening the studying of mathematics as symbol manipulation to studying music without ever hearing a note. So from that perspective, what do you think is mathematics? What is this world of mathematics like?
Well, I think of mathematics as a set of tools for exploring idealized worlds that often turn out to be extremely relevant to the real world, but need not. But they're worlds in which objects exist with idealized properties, and in which the relationships among them can be characterized with precision so as to allow the implications of certain facts to then allow you to derive other facts with certainty. So, if you have two triangles and you know that there is an angle in the first one that has the same measure as an angle in the second one, and you know that the lengths of the sides adjacent to that angle in each of the two triangles, the corresponding sides adjacent to that angle also have the same measure, then you can then conclude that the triangles are congruent. That is to say, they have all of their properties in common. And that is something about triangles. It's not a matter of formulas. These are idealized objects. In fact, we build bridges out of triangles, and we understand how to measure the height of something we can't climb by extending these ideas about triangles a little further. And, all of the ability to get a tiny speck of matter launched from the planet Earth to intersect with some tiny, tiny little body way beyond Pluto somewhere at exactly a predicted time and date is something that depends on these ideas, right? So, and it's actually happening in the real physical world that these ideas make contact with it in those kinds of instances. So, but there are these idealized objects, these triangles or these distances or these points, whatever they are, that allow for this set of tools to be created that then gives human beings it's this incredible leverage that they didn't have without these concepts. And I think this is actually already true when we think about just, the natural numbers. I always like to include zero, so I'm going to say the non-negative integers, but that's a place where some people prefer not to include zero. But
no, we like zero here. So natural numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on.
Yeah, and because they give you the ability to be exact about like how many sheep you have. Like, I sent you out this morning, there were 23 sheep. You came back with only 22. What happened?
Yeah.
Right?
The fundamental problem of physics, how many sheep you have. Yeah.
It's a fundamental problem of
life,
of human society, that you damn well better bring back the same number of sheep as you started with. And, it allows commerce, it allows contracts, it allows the establishment of records and so on, to have systems that allow these things to be notated. But they have an inherent aboutness to them that's at the one and the same time sort of abstract and idealized and generalizable, while on the other hand, potentially very, very grounded and concrete. And one of the things that makes for the incredible achievements of the human mind is the fact that humans invented these idealized systems that leverage the power of human thought in such a way as to allow all this kind of thing to happen. And so that's what mathematics to me is, the development of systems for thinking about the properties and relations among sets of idealized objects, and the mathematical notation system that we unfortunately focus way too much on is just our way of expressing propositions about these properties.
Right. It's just like we're talking with Chomsky in language. It's the thing we've invented for the communication of those ideas. They're not necessarily the deep representation of those ideas.
Yeah.
So what about looking at a particular characteristics of both physical ideas and mathematical ideas, which is beauty? Do you think beauty leads us astray? Meaning, and you offline showed me a really nice puzzle that illustrates this idea a little bit. Now, maybe you can speak to that, or another example where beauty makes it tempting for us to assume that the law and the theory we found is actually one that perfectly describes reality.
I think that beauty does not lead us astray, because I feel that beauty is a requirement for principles of physics.
So beauty is fundamental in the universe?
I think beauty is fundamental. At least that's the way many of us view it.
It's not emergent?
It's not emergent. I think Hardy is the mathematician who said that there's no permanent place for ugly mathematics. And so I think the same is true in physics, that if we find a principle which looks ugly, we are not going to be, that's not the end stage. So therefore, beauty is going to lead us somewhere. Now, it doesn't mean beauty is enough. It doesn't mean if you just have beauty, if I just look at something is beautiful, then I'm fine. No, that's not the case. Beauty is certainly a criteria that every good physical theory should pass. That's at least the view we have. Why do we have this view? That's a good question. It is partly, you could say, based on experience of science over centuries. Partly is a philosophical view of what reality is or should be. And in principle, it could have been ugly, and we might have had to deal with it, but we have gotten maybe confident through examples after examples in the history of science to look for beauty.
And our sense of beauty seems to incorporate a lot of things that are essential for us to solve some difficult problems, like symmetry. We find symmetry beautiful and the breaking of symmetry beautiful. Somehow symmetry is a fundamental part of how we conceive of beauty at all layers of reality, which is interesting. Like in both the visual space, like the way we look at art, we look at each other as human beings, the way we look at creatures in the biological space, the way we look at chemistry, and then into the physics world as the work you do. It's kind of interesting. It makes you wonder, like, which one is the chicken or the egg? Is symmetry the chicken and our conception of beauty the egg, or the other way around, or somehow the fact that the symmetry is part of reality it somehow creates the brain that then is able to perceive it? Or maybe this is just because maybe it's so obvious it's almost trivial that symmetry, of course, will be part of every kind of universe that's possible. And then any kind of organism that's able to observe that universe is going to appreciate symmetry.
Well, these are good questions. We don't have a deep understanding of why we get attracted to symmetry.
Yeah.
Why do laws of nature seem to have symmetries underlying them? And the reasoning or the examples of whether if there wasn't symmetry, we would have understood it or not. We could have said that, yeah, if there were things which didn't look that great, we could understand them. For example, we know that symmetries get broken, and we have appreciated nature in the broken symmetry phase as well. The world we live in has many things which do not look symmetric, but even those have underlying symmetry when you look at it more deeply. So we have gotten maybe spoiled perhaps by the appearance of symmetry all over the place, and we look for it. And I think this is perhaps related to the sense of aesthetics that scientists have, and we don't usually talk about it among scientists. In fact, it's kind of a philosophical view of why do we look for simplicity or beauty or so forth. And I think, in a sense, scientists are a lot like philosophers. Sometimes I think, especially modern science, seems to shun philosophers and philosophical views. Mm-hmm. And I think at their peril. I think, in my view, science owes a lot to philosophy. And in my view, many scientists, in fact, probably all good scientists, are perhaps amateur philosophers. Mm-hmm. They may not state that they are philosophers, or they may not like to be labeled philosophers, but in many ways what they do is like what is philosophical takes of things. Looking for simplicity or symmetry is an example of that, in my opinion. Or seeing patterns. You see, for example, another example of the symmetry is like how you come up with new ideas in science. You see, for example, an idea A is connected with an idea B. Okay, so you study this connection very deeply. And then you find the cousin of an idea A, let me call it A prime. And then you immediately look for B prime. If A is like B, and if there's an A prime, then you look for B prime. Why? Well, it completes the picture. Why? Well, it's philosophically appealing to have more balance in terms of that. And then you look for B prime, and lo and behold, you find this other phenomena, which is a physical phenomenon, which you call B prime. So this kind of thinking motivates asking questions and looking for things. And it has guided scientists, I think, through many centuries, and I think it continues to do the other.
Is there ways in which mathematics can lead us astray when we use it as a tool to understand the physical world?
Yes, I would say that mathematics can lead us astray as much as old physical ideas can lead us astray. So
true.
It is.
Yeah.
If you get stuck in something, then you can easily fool yourself that just like the thought process, we have to free ourselves of that. Sometimes math does that role. Like say, oh, this is such a beautiful math. I definitely want to use it somewhere. And so you just get carried away, and you just get maybe carried too far away. So that is certainly true. But I wouldn't say it's more dangerous than old physical ideas. To me, new math ideas is as much potential to lead us astray as old physical ideas, which could be long-held principles of physics. So I'm just saying that we should keep an open mind about the role the math plays, not to be antagonistic towards it, yeah, and not to over-welcoming it. We should just be open to possibilities.
You've practiced some of the most elegant formalism in computer science, and yet you're the creator of a concept like literate programming. which seems to move closer to natural language type of description of programming.
Yeah, absolutely.
So how do you see those two as conflicting, as the formalism of theory and the idea of literate programming?
So there we are in a non-uniform system where I don't think one size fits all, and I don't think all truth lies in one kind of expertise. And so somehow, in a way, you'd say my life is a convex combination of English and mathematics.
And you're okay with that?
And not only that, I think
thrive in it.
I wish, I want my kids to be that way. I want, et cetera. Not use left brain, right brain at the same time. You got a lot more done. That was part of the bargain.
And I've heard that you didn't really read for pleasure until into your 30s. Literature.
That's true. You know more about me than I do, but I'll try to be consistent with what you read.
Yeah, no, just believe me. I just go with whatever story I tell you. It'll be easier that way. The conversation will be
right. Yeah, no, that's true.
So I've heard mention of Philip Roth's American Pastoral, which I love as a book. I don't know if it was mentioned as something I think that was meaningful to you as well. In either case, what literary books had a lasting impact on you? What literature?
Yeah, okay, good
poetry?
question. So I met Roth.
Oh, really?
Well, we both got doctorates from Harvard on the same day. So we were, we had lunch together and stuff like that. But he knew that, computer books would never sell. Well, all right. So you say you were a teenager when you left Russia, so I have to say that Tolstoy was one of the big influences on me. I especially like Anna Karenina, not because of particularly of the plot of the story, but because there's this character who, the philosophical discussions that the whole way of life is worked out there among the characters, and so that I thought was especially beautiful. On the other hand, Dostoevsky, I didn't like at all because I felt that his genius was mostly because he kept forgetting what he had started out to do, and he was just sloppy. I didn't think that he polished his stuff at all, and I tend to admire somebody who dots the I's and crosses the T's.
So the music of the prose is what you admire more than...
I certainly do admire the music of the language, which I couldn't appreciate in the Russian original, but I can in Victor Hugo, because it's close. French is closer. But Tolstoy, I like the same reason I like Herman Wouk as a novelist. I think his book Marjorie Morningstar has a similar character in who developed his own personal philosophy and it goes in
was consistent.
Yeah, right.
Yeah.
And it's worth pondering. So
you don't like Nietzsche and
like what?
You don't like Friedrich Nietzsche or
Nietzsche? Yeah, no, yeah. This has I keep seeing quotations from Nietzsche, and they never tempt me to read any further.
Well, he's full of contradictions, so you will certainly not appreciate him.
But Schiller, I'm trying to get across what I appreciate in literature, and part of it is is as you say, the music of the language, the way it flows. And take Raymond Chandler versus Dashiell Hammett. Dashiell Hammett's sentences are awful, and Raymond Chandler's are beautiful. They just flow. So I don't read literature because it's supposed to be good for me or because somebody said it's great. But I find things that I like. I mean. You mentioned you were dressed like James Bond, so I love Ian Fleming. I think he had a really great gift for if he has a golf game or a game of bridge or something, and this comes into his story, it'll be the most exciting golf game or the absolute best possible hands of bridge that exists, and he exploits it and tells it beautifully.
So in connecting some things here, looking at literate programming and being able to convey, encode algorithms to a computer in a way that mimics how humans speak. What do you think about natural language in general and the messiness of our human world, about trying to express difficult things?
So the idea of literate programming is really to try to understand something better by seeing it from at least two perspectives, the formal and the informal. If we're trying to understand a complicated thing, if we can look at it in different ways. And so this is, in fact, the key to technical writing. A good technical writer, trying not to be obvious about it, but says everything twice, formally and informally, or maybe three times. But you try to give the reader a way to put the concept into his own brain or her own brain.
Is that better for the writer or the reader or both?
Well, the writer just tries to understand the reader. That's the goal of a writer, is to have a good mental image of the reader, and to say what the reader expects next, and to impress the reader with what has impressed the writer. Why something is interesting. So when you have a computer program, we try to, instead of looking at it as something that we're just trying to give an instruction to the computer, what we really want to be is giving insight to the person who's going to be maintaining this program, or to the programmer himself when he's debugging it, as to why this stuff is being done. And so all the techniques of exposition that a teacher uses or a book writer uses make you a better programmer if your program is going to be not just a one-shot deal.
So how difficult is that? Do you see hope for the combination of informal and formal for the programming task?
Yeah, I'm the wrong person to ask, I guess, because I'm a geek. But I think for a geek, it's easy. I don't know. Some people have difficulty writing, and that might be because there's something in their brain structure that makes it hard for them to write, or it might be something just that they haven't had enough practice. I'm not the right one to judge, but I don't think you can teach any person any particular skill. I do think that writing is half of my life, and so I put it together in literate program. Even when I'm writing a one-shot program, I write it in a literate way because I get it right faster that way.
Now, does it get compiled automatically, or? So I guess on the technical side, my question was, how difficult is it to design a system where much of the programming is done informally?
Informally?
Yeah, informally.
I think whatever works to make it understandable is good, but then you have to also understand how informal it is. You have to know the limitations. You have to so by putting the formal and informal together, this is where it gets locked into your brain. You can say informally, well, I'm working on a problem right now, so
let's go there. Can you give me an example of connecting the informal and the formal? So you mentioned dreaming. You've played around with some out there fascinating ideas. How do you think, and we'll start diving into the world of the very small ideas of supersymmetry and all that, sure, in terms of visualization, in terms of how do you think about it? How do you dream of it? How do you come up with ideas in that fascinating, mysterious space?
So in my workspace, which is basically where I am charged with coming up on a mathematical palette with new ideas that will help me understand the structure of nature and hopefully help all of us understand the structure of nature. I've observed several different ways in which my creativity expresses itself. There's one mode which looks pretty normal, which I sort of think of as the Chinese water torture method. It's drop, drop, drop. You get more and more information, and suddenly it all congeals, and you get a clear picture. And so that's a kind of a standard way of working. And I think that's how most people think about the way technical people solve problems. That it's kind of you accumulate this body of information, and at a certain point you synthesize it, and then boom, there's something new. But I've also observed in myself and other scientists that there are other ways that we are creative. And these other ways to me are actually far more powerful. I first personally experienced this when I was a freshman at MIT, live over in Baker House, right across the campus. And I was in a calculus course, 1801 is called at MIT. And calculus comes in two different flavors. One of them is called differential calculus. The other is called integral calculus. Differential calculus is the calculus that Newton invented to describe motion. It turns out integral calculus was probably invented about 1,700 years earlier by Archimedes, but we didn't know that when I was a freshman. But so that's what you study as a student. And the differential calculus part of the course was, to me, how do I say this? It was something that by the drip, drip, drip method, you could sort of figure it out. Mm-hmm. Now, the integral part of calculus, I could memorize the formula. That was not the formulae. That was not the problem. The problem was why, in my own mind, why do these formulae work? And because of that, when I was in the part of the calculus course where we had to do multiple substitutions to solve integrals, I had a lot of difficulty. I was emotionally involved in my education because this is where I think the passion emotion comes to. And it caused an emotional crisis that I was having these difficulties understanding the integral part of calculus.
The why.
Why. That's right. The why of it. Not the rote memorization of fact, but the why of it. Why does this work? And so one night I was over in my dormitory room in Baker House. I was trying to do a calculus problem set. I was getting nowhere. I got a terrific headache. I went to sleep and had this very strange dream. And when I awakened, I could do 3 and 4 substitutions in integrals with relative ease. Now, this to me was an astounding experience because I had never before in my life understood that one's subconscious is actually capable of being harnessed to do mathematics. I experienced this, and I've experienced this more than once. So this was just the first time why I remember it. So that's why when it comes to like really wickedly tough problems, I think that the kind of creativity that you need to solve them is probably this second variety, which comes somehow from dreaming.
Do you think, again, I told you I'm Russian, so we romanticize suffering. But do you think part of that equation is the suffering leading up to that dreaming?
So the suffering is, I am convinced that this kind of this second mode of creativity, as I like to call it, I'm convinced that this second mode of creativity is in fact that suffering is a kind of crucible that triggers it. Because the mind, I think, is struggling to get out of this, and the only way they can do is actually solve the problem. Yeah. And even though you're not consciously solving problems, something is going on. And I've talked to a few other people, and I've heard other similar stories. And so, the way I think about it is, it's a little bit like the way that thermonuclear weapons work. I don't know if you know how they work, but a thermonuclear weapon is actually 2 bombs. There's an atomic bomb, which sort of does a compression, and then you have a fusion bomb that goes off. And somehow that emotional pressure, I think, acts like the first stage of a thermonuclear weapon. That's when we get really big thoughts.
The analogy between thermonuclear weapons and the subconscious, the connection there is at least visually, it's kind of interesting.
Well,
there may be Freud would have a few things to say.
Well, part of it is probably based on my own trajectory through life. My father was in the Army for U.S. Army for 27 years, and so I started my life out on military bases. And so a lot of probably the things that wander around in my subconscious are connected to that experience.
I apologize for all the tangents, but
Well, you're doing it.
but you're encouraging it by answering the stupid questions.
No, they're not stupid.
Your father was in the Army. What do you think about Neil deGrasse Tyson recently wrote a book on interlinking the progress of science to sort of the aspirations of our military endeavors and DARPA funding and so on. What do you think about war in general? Do you think we'll always have war? Do you think we'll always have conflict in the world?
I'm not sure that we're going to be able to afford to have war always. Because if
strictly financially speaking?
No, not in terms of finance, but in terms of consequences. So if you look at technology today, you can have non-state actors acquire technology, for example, bioterrorism, whose impact is roughly speaking equivalent to what it used to take nations to impart on a population. Mm-hmm. I think the cost of war is ultimately, it's going to be I think it's going to work a little bit like the Cold War. We survived 50, 60 years as a species with these weapons that are so terrible that they could have actually ended our form of life on this planet, but it didn't. Why didn't it? Well, it's a very bizarre and interesting thing, but it was called mutually assured destruction. And so the cost was so great that people eventually figured out that you can't really use these things, which is kind of interesting because if you read the history about the development of nuclear weapons, physicists actually realized this pretty quickly. I think it was maybe Schrodinger who said that these things are not really weapons. They're political implements. They're not weapons because the cost is so high. And if you take that example and spread it out to the kind of technological development we're seeing now outside of nuclear physics, but I picked the example of biology. I could well imagine that there would be material science sorts of equivalents that across a broad front of technology, you take that experience from nuclear weapons, and the picture that I see is that it would be possible to develop technologies that are so terrible that you couldn't use them because the costs are too high, and that might cure us.
And many people have argued that actually nuclear weapons have prevented more military conflict than...
It certainly froze the conflict domain. It's interesting that nowadays it was with the removal of the threat of mutually assured destruction that other forces took over in our geopolitics.
If the brain is a cake...
It is?
Okay. Well, let's just go with me on this.
Okay, we'll pause it.
So for Noam Chomsky, language, the universal grammar, the framework from which language springs is like most of the cake, the delicious chocolate center. And then the rest of cognition that we think of is built on top, extra layers, maybe the icing on the cake, maybe just, maybe consciousness is just like a cherry on top. Where do you put in this cake mathematical thinking? Is it as fundamental as language in the Chomsky view? Is it more fundamental than language? Is it echoes of the same kind of abstract framework that he's thinking about in terms of language, that they're all like really tightly interconnected?
That's a really interesting question. You're getting me to reflect on this question of whether the feeling of producing mathematical output, if you want, is like the process of, uttering language, of producing linguistic output. I think it feels something like that, and it's certainly the case. Let me put it this way. It's hard to imagine doing mathematics in a completely non-linguistic way. It's hard to imagine doing mathematics without talking about mathematics and sort of thinking in propositions. But, maybe it's just because that's the way I do mathematics, and maybe I can't imagine it any other way, right?
Well, what about visualizing shapes, visualizing concepts to which language is not obviously attachable?
That's a really interesting question. And, one thing it reminds me of is one thing I talk about in the book is dissection proofs, these very beautiful proofs of geometric propositions. There's a very famous one by Bhaskara of the Pythagorean theorem. Proofs which are purely visual, proofs where you show that two quantities are the same by taking the same pieces and putting them together one way and making one shape, and putting them together another way and making a different shape, and then observing that those two shapes must have the same area because they were built out of the same pieces. There's a famous story, and it's a little bit disputed about how accurate this is, but that in Bhaskara's manuscript, he sort of gives this proof, just gives the diagram, and then the entire verbal content of the proof is he just writes under it, "Behold." Like, that's it. It's like, there's some dispute about exactly how accurate that is. But so then there's an interesting question. If your proof is a diagram, if your proof is a picture, or even if your proof is like a movie of the same pieces, like coming together in two different formations to make two different things, is that language? I'm not sure I have a good answer. What do you think?
I think it is. I think the process of manipulating the visual elements is the same as the process of manipulating the elements of language. And I think probably the manipulating, the aggregation, the stitching stuff together is the important part. It's not the actual specific elements. It's more like, to me, language is a process and math is a process. It's not just specific symbols. It's in action. It's ultimately created through action, through change. And so you're constantly evolving ideas. Of course, we kind of there's a certain destination you arrive to that you attach to, and you call that a proof. But that doesn't need to end there. It's just at the end of the chapter, and then it goes on and on and on. Let me ask the question.
Yes.
What to you is the most beautiful idea in physics or mathematics or the art at the intersection of the two?
I'm going to have to say complex analysis. I might have said infinities. And one of the most beautiful idea, I think, was the fact that you can have infinities of different sizes and so on. But that's, in a way, I think, complex analysis. It's got so much magic in it. It's a very simple idea. You take these, you take numbers, you take the integers, and then you fill them up into the fractions and the real numbers. You imagine you're trying to measure a continuous line. And then you think of how you can solve equations. Then what about x squared equals -1? Well, there's no real number which satisfies that. So you have to think of, well, there's a number called I. You think you invent it. Well, in a certain sense, it's there already. But this number, when you add that square root of -1 to it, you have what's called the complex numbers. And they're an incredible system. If you like, you put one little thing in, you put square root of -1 in, and you get how much benefit out of it. All sorts of things that you'd never imagined before. And it's that amazing, all hiding there in putting that square root of -1 in.
So in a sense,
I think that's the most magical thing I've seen in mathematics or physics. And it's in quantum mechanics.
And in quantum mechanics.
You see, it's there already. You might think, what's it doing there? Okay, just a nice, beautiful piece of mathematics. And then suddenly we see, nope. It's the very crucial basis of quantum mechanics.
So on
there in the way the world works.
So on the question of whether math is discovered or invented, it sounds like you may be suggesting that partially it's possible that math is indeed discovered.
Oh, absolutely. Yes. No, it's more like archaeology than you might think. Yes. Yes.
So let me ask the most ridiculous, maybe the most important question. What is the meaning of life? What gives your life fulfillment, purpose, happiness, and meaning? Why do you think we're here on this? Given all the Big Bang and the infinities of photons that we've talked about.
I would say, I think it's not a stupid question. I mean, there are some people, many of my colleagues who are scientists, and they say, well, that's a stupid question, meaning, well, we're just here because things came together and produced life and so what. I think there's more to it. But what there is that's more to it, I have really much idea.
And it might be somehow connected to the mechanisms of consciousness that we've been talking about, the mystery there.
Yeah. It's connected with all sorts of, I think these things are tied up in ways which are, you see, I tend to think the mystery of consciousness is tied up with the mystery of quantum mechanics and how it fits in with the classical world. And that's all to do with the mystery of complex numbers. And there are mysteries there which look like mathematical mysteries, but they seem to have a bearing on the way the physical world operates. We're scratching the surface. We have a long, huge way to go before we really understand that.
And it's a beautiful idea that the depth, the mathematical depth could be discovered. And then there's tragedies of Gödel's incompleteness along the way that we'll have to somehow figure our ways around.
Yeah.
So, Roger, it was a huge honor to talk to you. Thank you so much for your time today.
It's been my pleasure. Thank you.
Thanks for listening to this conversation with Roger Penrose. And thank you to our presenting sponsor, Cash App. Please consider supporting this podcast by getting ExpressVPN at expressvpn.com/LexPod and downloading Cash App and using code LEXPodcast. If you enjoy this podcast, subscribe on YouTube, review it with 5 stars on Apple Podcasts, support it on Patreon, or simply connect with me on Twitter at Lex Fridman. And now, let me leave you with some words of wisdom that Roger Penrose wrote in his book, The Emperor's New Mind. Beneath all this technicality is the feeling that it is indeed, quote-unquote, obvious that the conscious mind cannot work like a computer, even though much of what is involved in mental activity might do so. This is the kind of obviousness that a child can see, though the child may later in life become browbeaten into believing that the obvious problems are quote-unquote non-problems, to be argued into non-existence by careful reasoning and clever choices of definition. Children sometimes see things clearly that are obscured in later life. We often forget the wonder that we felt as children when the cares of the quote-unquote real world have begun to settle on our shoulders. Children are not afraid to pose basic questions that may embarrass us as adults to ask. What happens to each of our streams of consciousness after we die? Where was it before we were born? Might we become or have been someone else? Why do we perceive it all? Why are we here? Why is there a universe here at all in which we can actually be? These are puzzles that tend to come with the awakenings of awareness in any of us, and, no doubt, with the awakening of self-awareness within whichever creature or other entity it first came. Thank you for listening, and hope to see you next time. You're both a physicist and a mathematician. So let me ask, what is the difference between physics and mathematics?
Well, there's kind of a conventional understanding of the subject that they're two, quite different things. So that mathematics is about, making rigorous statements about these abstract things of mathematics and proving them rigorously. And physics is about, doing experiments and testing various models and that. But I think the more interesting thing is that there's a wide variety of what people do as mathematics, what they do as physics, and there's a significant overlap, and that I think is actually a much very, very interesting area. And if you go back kind of far enough to in history and look at figures like Newton or something, I mean, at that point you can't really tell, was Newton a physicist or a mathematician? The mathematicians will tell you he's a mathematician, the physicists will tell you he's a physicist, but
he would say he's a philosopher.
That's interesting. But anyway, there was kind of no such distinction then. It's more of a modern thing. But anyway, I think these days there's a very interesting space in between the two.
So in the story of the 20th century and the early 21st century, what is the overlap between mathematics and physics, would you say?
Well, I think it's actually become very, very complicated. I think it's really interesting to see a lot of what my colleagues in the math department are doing. Most of what they're doing all sorts of different things, but most of them have some kind of overlap with physics or other. So, I mean, I'm personally interested in one particular aspect of this overlap, which I think has a lot to do with the most fundamental ideas about physics and about mathematics. But there's just you kind of see this really everywhere at this point.
Which particular overlap are you looking at? Group theory?
Yeah. So at least the way it seems to me, that if you look at physics and look at our most successful laws of fundamental physics, they're really, they have a certain kind of mathematical structure. It's based upon certain kind of mathematical objects and geometry, connections and curvature, the spinors, the Dirac equation, and this very deep mathematics provides kind of a unifying set of ways of thinking that allow you to make a unified theory of physics. But the interesting thing is that if you go to mathematics and look at what's been going on in mathematics the last 50, 100 years, and even especially recently, there's similarly some kind of unifying ideas which bring together different areas of mathematics, and which have been especially powerful in number theory recently. And there's a book, for instance, by Edward Frankel about love and math. And
oh yeah, that book's great. I recommend it highly. It's partially accessible, but there's a nice audiobook that I listened to while running an exceptionally long distance, like across the San Francisco bridge. And there's something magic about the way he writes about it. But some of the group theory in there is a little bit difficult.
Yeah, it's a problem with any of these things. To kind of really say what's going on and make it accessible is very hard. He, in this book and elsewhere, I think, takes the attitude that kinds of mathematics he's interested in and that he's talking about provide kind of a grand unified theory of mathematics. They bring together geometry and number theory and representation theory, a lot of different ideas in a really unexpected way. But I think to me, the most fascinating thing is if you look at the kind of grand unified theory of mathematics he's talking about, and you look at the physicists' kind of ideas about unification, it's more or less the same mathematical objects are appearing in both. So it's this, I think we're seeing a really strong indication that, the deepest ideas that we're discovering about physics and some of the deepest ideas that mathematicians are learning about are intimately connected.
Is there something, like, if I was 5 years old and you were trying to explain this to me, is there ways to try to sneak up to what this unified world of mathematics looks like? You said number theory, you said geometry, words like topology. What does this universe begin to look like? What should we imagine in our mind? Is it a three-dimensional surface and we're trying to say something about it? Is it triangles and squares and cubes? Like, what are we supposed to imagine in our minds? Is this natural number? What's a good thing to try for people that don't know any of these tools except maybe some basic calculus and geometry from high school, that they should keep in their minds as to the unified world of mathematics that also allows us to explore the unified world of physics?
What I find kind of remarkable about this is the way in which we've discovered these ideas, but they're actually quite alien to our everyday understanding. We grow up in this three spatial dimensional world, and we have intimate understanding of certain kinds of geometry and certain kinds of things. But these things that we've discovered in both math and physics they're not at all close, have any obvious connection to kind of human everyday experience. They're really quite different. And I can say some of my initial fascination with this when I was young and starting to learn about it was actually exactly this this kind of arcane nature of these things. It was a little bit like being told, well, there are these kind of semi-mystical experience that you can acquire by long study and whatever, except that it was actually true. There's actually evidence that this actually works. So I'm a little bit wary of trying to give people that kind of thing because I think it's mostly misleading. But one thing to say is that that geometry is a large part of it, and maybe one interesting thing to say that's about some of the most recent ideas is that when we think about the geometry of our space and time, it's kind of three spatial and one time dimension. It's physics is in some sense about something that's kind of four-dimensional in a way. Mm-hmm. And that a really interesting thing about some of the recent developments in number theory have been to realize that these ideas that we were looking at, naturally fit into a context where your theory is kind of four-dimensional. So geometry is a big part of this, and we know a lot and feel a lot about 1, 2, 3-dimensional geometry.
So wait a minute. So we can at least rely on the 4 dimensions of space and time and say that we can get pretty far by working in those 4 dimensions. I thought you were going to scare me that we're going to have to go to many, 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 many more dimensions than that.
My point of view, which goes against a lot of these ideas about unification, is that no, this is really everything we know about really is about 4 dimensions, that and that you can actually understand a lot of these structures that we've been seeing in fundamental physics and in number theory just in terms of 4 dimensions. That it's in some sense, I would claim, has been kind of a mistake that physicists have made for decades and decades to try to go to higher dimensions, to try to formulate a theory in higher dimensions, and then you're stuck with the problem of how do you get rid of all these extra dimensions that you've created, and because we only ever see anything in 4 dimensions.
That kind of thing leads us astray, you think? So creating all these extra dimensions just to give yourself extra degrees of freedom.
Yeah.
Isn't that the process of mathematics, is to create all of these trajectories for yourself, but eventually you have to end up at like a final place. But it's okay to sort of create abstract objects on your path to proving something.
Yeah, certainly. And from mathematicians' point of view, I mean, the kinds of mathematicians also are very different than physicists in that we like to develop very general theories. We like to, if we have an idea, we want to see what's the greatest generality in which you can talk about it. Mm-hmm. So from the point of view of most of the ways geometry is formulated by mathematicians, it really doesn't matter. It works in any dimension. We can do 1, 2, 3, 4, any number. There's no particular, for most of geometry, there's no particular special thing about 4. But and anyway, but what physicists have been trying to do over the years is try to understand these fundamental theories in a geometrical way, and it's very tempting to kind of just start bringing in extra dimensions and using them to explain the structure. But it typically this attempt kind of founders because you just don't know. You end up not being able to explain why we only see 4. And anyway.
It is nice in the space of physics that, like if you look at Fermat's last theorem, it's much easier to prove that there's no solution for n equals 3 than it is for the general case. And so I guess that's the nice benefit of being a physicist, is you don't have to worry about the general case because we live in a universe with n equals 4 in this case.
Yeah, physicists are very interested in saying something about specific examples. And I find that interesting even when I'm trying to do things in mathematics, and I'm even teaching courses to mathematics students, I find that I'm teaching them in a different way than most mathematicians, because I'm very often very focused on examples, on what's kind of the crucial example that shows how this powerful new mathematical technique, how it works and why you would want to do it. And I'm less interested in kind of, proving a precise theorem about exactly when it's going to work and when it's not going to work.
Do you usually think about really simple examples, like both for teaching and when you try to solve a difficult problem? Do you construct like the simplest possible examples that captures the fundamentals of the problem and try to solve it?
Yeah, exactly. That's often a really fruitful way to, if you've got some idea, to just kind of try to boil it down to what's the simplest situation in which this kind of thing is going to happen, and then try to really understand that, and that is almost always a really good way to get insight into.
Do you work with paper and pen, or like, for example, for me, coming from the programming side, if I look at a model, if I look at some kind of mathematical object, I like to mess around with it sort of numerically. I just visualize different parts of it, visualize however I can. So most of the work is like with neural networks, for example, is you try to play with the simplest possible example and just to build up intuition by, any kind of object has a bunch of variables in it. Yeah. And you start to mess around with them in different ways and visualize in different ways to start to build intuition. Or do you go the Einstein route and just imagine like everything inside your mind and sort of build like thought experiments and then work purely on paper and pen?
Well, the problem with this kind of stuff that I'm interested in is you rarely can kind of, it's rarely something that is really kind of, or even the simplest example, you can kind of see what's going on by looking at something happening in 3 dimensions. Right. There's generally the structures involved are either they're more abstract, or if you try to kind of embed them in some kind of space and where you could manipulate them in some kind of geometrical way, it's going to be a much higher dimensional space.
So even simple examples, the embedding them into three-dimensional space, you're losing a lot.
Yeah, but to capture what you're trying to understand about them, you have to go to 4 or more dimensions. So it starts to get to be hard to. I mean, you can train yourself to try it as much as to kind of think about things in your mind. And I often use pad and paper, and if I'm in my office, I often use the blackboard. And you are kind of drawing things, but they're really kind of more abstract representations of how things are supposed to fit together, and they're not really, unfortunately, not just kind of really living in 3 dimensions where you can.
Are we supposed to be sad or excited by the fact that our human minds can't fully comprehend the kind of mathematics you're talking about? I mean, what do we make of that? I mean, to me, that makes me quite sad. It makes it seem like there's a giant mystery out there that we'll never truly get to experience directly.
It is kind of sad, how difficult this is. I mean, or I would put it a different way, that, most questions that people have about this kind of thing, you can give them a really a true answer and really understand it. But the problem is one more of time. It's like, yes, I could explain to you how this works, but you'd have to be willing to sit down with me and work at this repeatedly for hours and days and weeks. And it's just going to take that long for your mind to really wrap itself around what's going on. And that does make things inaccessible, which is sad. But it's just kind of part of life that we all have a limited amount of time, and we have to decide what we're gonna spend our time doing.
Speaking of a limited amount of time, we only have a few hours, maybe a few days together here on this podcast. And let me ask you the question of, amongst many of the ideas that you work on in mathematics and physics, what to you is the most beautiful idea, or one of the most beautiful ideas, maybe a surprising idea? And once again, unfortunately, the way life works, we only have a limited time together to try to convey such an idea.
Okay. Well, actually, let me just tell you something which I'm tempted to kind of start trying to explain what I think is this most powerful idea that brings together math and physics, ideas about groups and representations and how it fits in quantum mechanics. But in some sense, I wrote a whole textbook about that, and I don't think we really have time to get very far into it. So,
well, can I actually, on a small tangent, you did write a paper towards the Grant Unified Theory of Mathematics and Physics. Maybe you could step there first. What is the key idea in that paper?
Well, I think we've kind of gone over that. I think that the key idea is what we were talking about earlier, that just kind of a claim that if you look and see have been successful ideas in unification in physics over the last 50 years or so, and what has been happening in mathematics, and the kind of thing that Frankel's book is about, that these are very much the same kind of mathematics. And so it's kind of an argument that there really is, you shouldn't be looking to unify just math or just fundamental physics, but taking inspiration for looking for new ideas in fundamental physics, that they are going to be in the same direction of getting deeper into mathematics, and looking for more inspiration in mathematics from these successful ideas about fundamental physics.
Could you put words to sort of the disciplines we're trying to unify? So you said number theory. Are we literally talking about all the major fields of mathematics? So it's like the number theory, geometry, like differential geometry, topology. Like,
yeah. So one name for this, that this is acquired in mathematics, is the so-called Langlands program. Mm-hmm. And so this started out in mathematics. It's that, Robert Langlands kind of realized that a lot of what people were doing that was starting to be really successful in number theory in the 60s. And so that this actually was, anyway, that this could be thought of in terms of these ideas about symmetry in groups and representations, and in a way that was also close to some ideas about geometry. And then more later on in the 80s and 90s, there was something called geometric Langlands, that people realized that you could take what people have been doing in number theory in Langlands and and just forget about the number theory and ask, what is this telling you about geometry? And you get some new insights into certain kinds of geometry that way. So anyway, that's kind of the name for this area, is Langlands and geometric Langlands. And just recently, in the last few months, there's been there's kind of a really major paper that appeared by Peter Schulze and Laurent Fargue, where they, made a serious advance in trying to understand a very much kind of a local problem of what happens in number theory near a certain prime number, and they turn this into a problem of exactly the kind that geometric Langlands people had been doing, these kind of a pure geometry problem, and they found by generalizing the mathematics they could actually reformulate it in that way, and it worked perfectly well. So.
One of the things that makes me sad is, I'm a pretty knowledgeable person what is it? At least I'm in the neighborhood of like theoretical computer science, right? And it's still way out of my reach. And so many people talk about, like, Langlands, for example, is one of the most brilliant people in mathematics, and just really admire his work. And it's like almost I can't hear the music that he composed, and it makes me sad.
Yeah. Well, I mean, I think that unfortunately it's not just you. It's, I think, even most mathematicians really don't actually understand what this is about. I mean, the group of people who really understand all these ideas. And so, for instance, this paper of Schulze and Fargue that I was talking about, the number of people who really actually understand how that works is, anyway, very, very small. And so I think even you find, if you talk to mathematicians and physicists, even they will often feel that, there's this really interesting sounding stuff going on, and which I should be able to understand. It's kind of in my own field I have a PhD in, but it still seems it's pretty clearly far beyond me right now.
Well, if we can step back to the question of beauty, is there an idea that maybe is a little bit smaller that you find beautiful in the space of mathematics or physics?
There's an idea that, I kind of got a physics PhD and spent a lot of time learning about mathematics. And I guess it was embarrassing that I hadn't really actually understood this very simple idea until and kind of learned it when I actually started teaching math classes, which is maybe maybe there's a simple way to explain kind of the fundamental way in which algebra and geometry are connected. So you normally think of geometry as about these spaces and these points, and you think of algebra as this very abstract thing with these abstract objects that satisfy certain kinds of relations. You can multiply them and add them and do stuff, but it's completely abstract. There's nothing geometric about it. But the kind of really fundamental idea is that unifies algebra and geometry is to think whenever anybody gives you what you call in algebra some abstract thing of things that you can multiply and add, that you should ask yourself, is that algebra the space of functions on some geometry? So one of the most surprising examples of this, for instance, is a standard kind of thing that seems to have nothing to do with geometry is the integers. So you can multiply them and add them. It's an algebra, but seems to have nothing to do with geometry. But it turns out, but if you ask yourself this question and ask, are integers, can you think, if somebody gives you an integer, can you think of it as a function on some space, on some geometry? And it turns out that yes, you can. And the space is the space of prime numbers. And so what you do is if somebody gives you an integer, you can make a function on the prime numbers by just, at each prime number, taking that integer modulo that prime. So if you say, I don't know, if you're given 10, 10, and you ask what is its value at 2, well, it's 5 times 2, so mod 2, it's 0, so it has 0, 1. What is its value at 3? Well, it's 9 plus 1, so it's 1 mod 3. So it's 0 at 2, it's 1 at 3, and you can kind of keep going. And so this is really kind of a truly fundamental idea. It's at the basis of what's called algebraic geometry, and it just links these two parts of mathematics that look completely different. And it's just an incredibly powerful idea, and so much of mathematics emerges from this kind of simple relation.
So you're talking about mapping from one discrete space to another. So for a second, I thought perhaps mapping like a continuous space to a discrete space, like functions over a continuous space. Because
Well, you can take, if somebody gives you a space, you can say, well, let's, and this is part of the same idea. The part of the same idea is that if you try and do geometry and somebody tells you, here's a space, that what you should do is you should wait a minute, maybe I should be trying to solve this using algebra. And so if I do that, the way to start is you give me the space, I start to think about the functions in the space. Okay. So to each point in the space, I associate a number. I can take different kinds of functions and different kinds of values, but basically functions on a space. So what this insight is telling you is that if you're a geometer, often the way to work is to change your problem into algebra by changing your space. Stop thinking about your space and the points in it and think about the functions on it.
Got it.
And if you're an algebraist and you've got these abstract algebraic gadgets that you're multiplying and adding, say, wait a minute, are those gadgets, can I think of them in some way as a function on a space? What would that space be? And what kind of functions would they be? And that going back and forth really brings these two completely different looking areas of mathematics together.
Do you have particular examples where it allowed to prove some difficult things by jumping from one to the other? Is that something that's a part of modern mathematics where such jumps are made?
Oh, yeah. So this is kind of all the time. Much of modern number theory is kind of based on this idea. But, and when you start doing this, you start to realize that you need, what simple things on one side in algebra, start to require you to think about the other side, about geometry in a new way. You have to kind of get a more sophisticated idea about geometry. Or if you start thinking about the functions on a space, you may need a more sophisticated kind of algebra. But in some sense, much or most of modern number theory is based upon this move to geometry. And there's also a lot of geometry and topology is also based upon change. If you want to understand the topology of something, you look at the functions, you do de Rham cohomology, and you get the topology. Yeah. Anyway.
Well, let me ask you then the ridiculous question. You said that this idea is beautiful. Can you formalize a definition of the word beautiful? And why is this beautiful? Like, first, why is this beautiful? And second, what is beautiful?
Yeah, well, I think there are many different things you can find beautiful for different reasons. I think in this context, the notion of beauty, I think really is just kind of that an idea is beautiful if it packages a huge amount of kind of power and information into something very simple. So in some sense, you can almost kind of try and measure it in the sense of, what are the implications of this idea? What non-trivial things does it tell you versus, how simply can you express the idea? And so
the level of compression,
yeah.
What is it? Correlates with beauty.
Yeah, that's one aspect of it. Mm-hmm. And so you can start to tell that an idea is becoming uglier and uglier as you start kind of having to, it doesn't quite do what you want. So you throw in something else to the idea and you keep doing that until you get what you want. But that's how you know you're doing something uglier and uglier, when you have to kind of keep adding in more into what was originally a fairly simple idea and making it more and more complicated to get what you want.
Okay, so let's put some philosophical words on the table and try to make some sense of them. One word is beauty. Another one is simplicity, as you mentioned. Another one is truth. Yeah. So do you have a sense, if I give you two theories, one is simpler, one is more complicated, do you have a sense of which one is more likely to be true, to capture deeply the fabric of reality? The simple one or the more complicated one?
I think all of our evidence, what we see in the history of the subject, is the simpler one, though often it's a surprise. It's simpler in a surprising way, but that we just don't. Anyway, when the kind of best theories we've been coming up with are ultimately, when properly understood, relatively simple, and much, much simpler than you would expect them to be.
Do you have a good explanation why that is? Is it just because humans want it to be that way? Are we just like ultra biased and we just kind of convince ourselves that simple is better because we find simplicity beautiful? Or is there something about our actual universe that at the core is simple?
My own belief is that there is something about a universe that's simple, and I was trying to say that there is some kind of fundamental thing about math, physics, and all this picture, which is which is in some sense simple. I mean, it's true that it's of course true that our minds are very limited and can certainly do certain things and not others. So it's in principle possible that there's some great insight. There are a lot of insights into the way the world works, which aren't accessible to us because that's not the way our minds work. We don't, and that what we're seeing, this kind of simplicity, is just because that's all we ever have any hope of seeing. But
so there's a brilliant physicist by the name of Sabine Hassenfelder who both agrees and disagrees with you. I suppose agrees that the final answer will be simple.
Yeah.
But simplicity and beauty leads us astray in the local pockets of scientific progress. Do you agree with her disagreement? Do you disagree with her agreement? And agree with the agreement?
Yes, I found it was really fascinating reading her book, and anyway, I was finding disagreeing with a lot, but then at the end when she says yes, when we find when we actually figure this out, it will be simple, and okay, so we agree in the end.
But does beauty lead us astray, which is the core thesis of her work in that book?
I guess I do disagree with her on that so much. I don't think, and especially, and I actually fairly strongly disagree with her about sometimes the way she'll refer to math. And so the problem is, physicists and people in general just refer to it as math, and they're often they're often meaning not what I would call math, which is the interesting ideas of math, but just some complicated calculation. And so I guess my feeling about it is more that it's very. The problem with talking about simplicity and using simplicity as a guide is that it's very easy to fool yourself, and it's very easy to decide to fall in love with an idea. You have an idea, you think, oh, this is great, and you fall in love with it, and it's like any kind of love affair. It's very easy to believe that the object of your affections is much more beautiful than others might think, and that they really are, and that's very, very easy to do. So if you say, I'm just going to pursue ideas about beauty and this and mathematics and this, it's extremely easy to just fool yourself, I think. And I think that's a lot of what the story she was thinking of about where people have gone astray. That I would argue that it's more people. It's not that there was some simple, powerful, wonderful idea which they'd found and it turned out not to be useful, but it was more that they kind of fooled themselves that this was actually a better idea than it really was, and that it was simpler and more beautiful than it really was, is a lot of the story.
I see. So it's not that the simplicity of beauty leads us astray, is that just people are people and they fall in love with whatever idea they have, and then they weave narratives around that idea, or they present it in such a way that emphasizes the simplicity and the beauty.
Yeah, that's part of it. But I mean, the thing about physics that you have is that what really can tell, if you can do an experiment and check and see if nature is really doing what your idea expects, that you do in principle have a way of really testing it. And it's certainly true that if you thought you had a simple idea and that doesn't work, and you go out and do an experiment, and what actually does work is maybe some more complicated version of it, that can certainly happen, and that can be true. I think her emphasis is more, that I don't really disagree with, is that people should be concentrating on, when they're trying to develop better theories, more on self-consistency, not so much on beauty, but not is this idea beautiful, but is there something about the theory which is not quite consistent, and use that as a guide that there's something wrong there which needs fixing, and so I think that part of her argument, I think we're on the same page about.
What is consistency and inconsistencies? What exactly? Do you have examples in mind?
Well, it can be just simple inconsistency between theory and experiment. So we have this great fundamental theory, but there are some things that we see out there which don't seem to fit in it, like dark energy and dark matter, for instance. But if there's something which you can't test experimentally, I think, she would argue, and I would agree, that, for instance, if you're trying to think about gravity and how are you going to have a quantum theory of gravity, you should kind of test any of your ideas with kind of a thought experiment. Does this actually give a consistent picture of what's going to happen, of what happens in this particular situation or not?
So this is a good example. You've written about this. Since quantum gravitational effects are really small, super small, arguably unobservably small, should we have hope to arrive at a theory of quantum gravity somehow? What are the different ways we can get there? You've mentioned that you're not as interested in that effort because basically, yes, you cannot have ways to scientifically validate it given the tools of today.
Yeah. I've actually, I've over the years certainly spent a lot of time learning about gravity and about attempts to quantize it, but it hasn't been that much in the past the focus of what I've been thinking about. But I mean, my feeling was always, as I think Sabina would agree, that the one way you can pursue this if you can't do experiments is just this kind of search for consistency. It can be remarkably hard to come up with a completely consistent model of this in a way that brings together quantum mechanics and general relativity. And that's, I think, kind of been the traditional way that people who have pursued quantum gravity have often pursued, we have the best route to finding a consistent theory of quantum gravity. And string theorists will tell you this. Other people will tell you it's kind of what people argue about. But the problem with all of that is that you end up, the danger is that you end up with that everybody could be successful. Everybody's program for how to find a theory of quantum gravity, ends up with something that is consistent. And so, in some sense, you could argue this is what happened to the string theorists. They solved their problem of finding a consistent theory of quantum gravity, and but they found 10 to the 500 solutions. So, if you believe that everything that they would like to be true is true, well, okay, you've got a theory, but it ends up being kind of useless because it's just one of an essentially infinite number of things which you have no way to experimentally distinguish. And so this is just a depressing situation. But I do think that there is a so again, I think pursuing ideas about more about beauty and how can you integrate and unify these issues about gravity with other things we know about physics, and can you find a theory where these fit together in a way that makes sense and hopefully predict something that's much more promising.
Well, it makes sense, and hopefully, we'll sneak up onto this question a bunch of times because you kind of said a few slightly contradictory things, which is like, it's nice to have a theory that's consistent, but then if the theory is consistent, it doesn't necessarily mean anything. So like,
it's not enough. It's not enough.
It's not enough. And that's the problem. So it's like, it keeps coming back to, okay, there should be some experimental validation.